So I'd like to thank the organizers for inviting me to this conference in honor of Bala. And Bala has been a truly inspiring figure in Indian science. I mean, he started working on the subject of gravitational waves when very few people are working on it internationally. And since then, he has continued to make not only major scientific contributions, but he has also developed the gravitational wave group in India. So thank you, Bala, for all your contributions. So my talk today will be on the discussion of gravitational waves from soft theorem. It will be perhaps in a very different spirit from all the talks that has been in the morning, okay, because I'll be trying to address somehow different kinds of problems. So the goal will be to summarize the results on gravitational waves from soft theorem. I'll not make any attempt to give any derivation because that will take a long time. And these will be of two kinds. First, I'll describe, well, they will come together. Okay, that the first point will be the new viewpoint for older results, okay, in particular the memory effect from the point of view of soft theorem. This was initiated by Strominger, and then many more people have contributed to it. And then I'll describe some new results that one can get from soft theorem. This is what is called subleading soft theorem. And these will describe my work with Alok, who is in CMI, and Biswajit Sahu, who is a graduate student at HRI. So let's consider the problem where you have an explosion in space. So imagine a bound system at rest breaks apart into fragments which carry 4 momenta p1, p2, etc. of different masses. This bound system can be a binary black hole system or a supernova, okay, or a black hole neutron star system. We don't make any assumption about what this system was. For simplicity, we'll assume that the original bound system was at rest, but this is not a necessary assumption. So here are the relations that the energy and the momentum of the fragments have to satisfy. This is the usual mass cell condition. And because the original system was at rest, the sum of the spatial momenta should be 0. So this process will emit gravitational waves. And if we have a detector D that's placed far away, it will detect the fluctuation in the gravitational field, which I'll denote by h mu nu.
This is all in Minkowski.
Pardon?
This all is
in Minkowski space, yes. Asymptotically in Minkowski space. Well, asymptotically you can measure the momenta, right? Yes. The bound particles?
The particles are not coming in from infinity.
No, but you are measuring momentum from infinity. So what I'm saying, this is you can measure the energy and momentum, right, from infinity, asymptotic infinity, because the particles are inside.
So these are asymptotic values of momenta, is it?
Yes, that's right. So these are asymptotic values of momenta, exactly. So these are momenta of the final state particles which are all dispersed, which could include, for example, a remnant black hole, right? That also we'll think of as a particle, which is one of the, so in the momentum of the remnant black hole will be one of these. Okay, so our focus will be on the late time tail of the radiation, namely the value of the gravitational field at a large time u after the passage of the peak of the gravitational wave. So this u you can think of as a retarded time. And this waveform has the following structure at large u. It has an expansion in powers of 1 over u. This term is the constant term. This is what is called the memory term. This reflects a permanent change in the state of the detector after the passage of the gravitational waves. And this is connected to the leading soft graviton theorem. And this is what was discussed by Strominger and various other authors. This coefficient is what I'll call the tail term. And this is connected to the logarithmic terms in the subleading soft theorem. And the main result from the soft theorem is that these coefficients A and B can be determined solely in terms of the momenta of the final state particles. So A mu nu is given by this expression over here. So let me explain the various terms. G here is the Newton's constant. R is a distance to the detector from the place where the explosion is taking place, and we are working the large R limit. The dot product is the usual dot product with mostly positive signature metric. And this n is a 4 vector whose first component is 1 and the spatial component is simply the unit vector towards the detector. Okay, so it's basically the vector that points from the center of explosion towards the detector. So this is the main formula that comes out of soft theorem, and in the rest of the talk I'll be describing various properties and consequences of this formula. So here is the formula again. Now the first point I'd like to make is that if a significant fraction of the energy is carried away by radiation, then the sum over A and B, which usually is the sum over final state particles, should also include integration over the outgoing flux of radiation, and in this we'll regard the radiation just as a flux of massless particles. Okay, so this is a well-defined quantity. It will involve some integrals rather than just sums. Yes. Well, because we are looking at r goes to infinity limit, because you are going to the r goes to infinity limit, n is a well-defined object, right? Because most of the space-time is Minkowskian, right? So imagine that there is a region which is not Minkowskian, but the distance at which you are measuring, placing the detector is far away. Okay, so here are some more points about this formula. So first, the result is a statement in classical GR. Even though it was derived using soft graviton theorem or a result for S matrix, okay, so you start from the S matrix and then take various limits to arrive at the result, okay, but the statement itself is a statement in classical GR, okay, there is a quantum physics here. The second point that I have already mentioned is that the result is given completely in terms of the momenta of final state objects without knowing what caused the explosion or how the objects moved during the explosion. Okay, and this again is a consequence of the soft graviton theorem. The third point, about which I'll mention more later, is what one can show from here is that the contribution to this B from massless particles, I said that you can include massless particles in this sum, but the contribution from B from massless particles actually vanish. And that vanishing is a consequence of a cancellation between terms that come from here and the first term over here. Okay, it's not obvious from this formula, but when you do the calculation, you will find that the contribution from the massless particles actually vanish. So it turns out that there is a similar result that exists for a general scattering process. Okay, so let me explain the general scattering process. So here we assume that there are a set of particles coming in and a set of particles going out. So this perhaps also addresses some of the question, one of the questions that was asked this morning, that if we take a neutron star which goes close to the black hole, okay, and scatters, what kind of radiation comes out? Of course, we don't know the full details of the radiation, but at least the asymptotic form of the radiation is contained in this formula. So for the scattering problem, it's easier to describe the result in the Fourier space. Okay. So instead of describing this as a function of the retarded time variable u, okay, we describe this as a function of the Fourier transform, the frequency space, omega. Okay. So the transverse traceless component of the Fourier transform of the gravitational wave form, okay, is what I'll callCijtt, okay, and this is the expression for C mu nu. Okay. So in this expression, okay, so this 1 is a leading term, this is what reflects the memory term, okay, after Fourier transform. Okay. The rest of the terms, which are proportional to log of omega, okay, these describe the one where you fall off. Okay, well, again, this Fourier transform is being done in the asymptotic space, right? In sky, exactly. That's right. Because this, what we are measuring here, right, is really in at sky plus.
X is what then?
Okay, instead of x, we can write n. Okay? This is a direction, triangular direction. In sky plus, you have the theta phi variable, right?
Okay, but there's no relation between x and k. I mean, k I understand, which is the direction in sky.
K is defined by this. Okay, n x, maybe I can write this n hat is just x over r, and r is mod x. Yes, the whole thing refers to Sky, exactly. Right? We are measuring in Sky plus, and this R enters, this is the usual 1 over R in the radiation formula, right? Because we are looking at R distance away from the center of scattering. Okay, now this, as I said, was derived from soft theorem, but of course one can ask, how do you know this is correct? Okay, because you have done various things. You have started with the quantum formula, then taken the classical limit, and so on. Okay, but you can check this against various known results. Okay, and this is what we had done. In fact, there are old results by Peters in the 70s where he actually calculates the scattering of a particle from a black hole. Okay, and we have checked that the late time, or in the Fourier transform, the log omega piece of his answer exactly matches with what we have here. Okay, so in spatial cases, this does reproduce what we calculate in classical gravity. There is a more recent calculation by these authors, okay, where they looked at two nearly massless particles scattering, okay, and calculated the gravitational radiation from that process. And again, in the soft limit, in the small omega limit, this formula exactly reproduces that formula. Okay, so that gives confidence that the result is correct. As I have already said, we will not attempt to explain these results from soft graviton theorem because that will take us a long way. Okay. But let me just say that this, what we are trying to calculate, okay, the large U behavior, okay, is related to non-analytic behavior in the Fourier space. Okay. So what we are looking for, okay, in this formula are non-analytic terms for small omega. Okay. And typically in S matrix, the non-analytic terms are related to infrared singularities. And those are much easier to calculate than the full S matrix. Okay, and that's what we exploit. And the universality of this formula, the fact that the formula can be written down just in terms of the final state particles, or for the scattering, just in terms of the momenta and momenta of the final state and initial state particles, is just a reflection of the fact that in the S matrix we are looking for singular terms in the infrared limit. Okay, so what I'll do in the rest of the talk, which may be 2 minutes, will be to try to explain how these various parts of B mu nu might arise in a classical GR analysis. Okay, so suppose you forget about soft theorem and just try to see if these could arise in a classical GR analysis. So this is what we'll try to explain. The memory term, of course, is well understood in classical GR, so I have nothing more to say about the memory term. So recall that B mu nu has two terms, the first and the second term. Okay, and these turn out to have very different origin in the classical GR. Okay, so I'll try to explain what the origin of these two terms are. So suppose you have an explosion. So after the explosion, the final state's objects will exert long-range gravitational force on each other, and that causes them to accelerate. Okay, so even when the particles have gone far away from each other and gravity is weak, they still are under each other's gravitational influence, and as a result, they continue to accelerate or decelerate. Because of this acceleration or deceleration, they continue to radiate. And this radiation, this late time radiation, okay, seems to lead to the second term in B mu nu that is proportional to this complicated formula over here. So the second term has its origin because of this late time acceleration of the particles that are flying off. And both massive and massless particles contribute to this. Okay, you can see that when you set m equal to 0, this gives a non-zero result. The other effect comes from the observation that the component of the gravitational wave that is associated with the memory effect, this will have to travel in the background geometry of the hard particles or radiation, okay, namely the particles which are flying away, before they actually reach the detector. Okay. So there is backscattering. Okay, the Green's function that you have to use to calculate the propagation of these particles, their radiation to Sky plus, is not the usual iterative Green's function in Minkowski space, but you have to calculate the Green's function in the background of these other particles. And this is what seems to be responsible for the first term in B mu nu that is proportional to this combination over here. So the main task that is left for a direct GR proof, okay, is not to get these terms, okay, but to actually show that there are no other effects to this order. Okay, and that is what we are currently working on, to make sure that these are the only two effects that we have in this large time limit. Now, the fact that these two terms have different origins is also visible in the analysis based on the soft theorem. Okay, this is my last slide, so I'll be done soon. So the first term, namely this one, this comes from loop momenta. Sorry, not this term. The first term is this one. Okay, in the expression for B mu nu, this was the first term. So this term comes from loop momentum that is less than 1 over u. While the second term, which is the more complicated one, comes from loop momentum larger than 1 over u. Okay, so these two terms really have different origin, okay, both in classical GR analysis as well as in the soft theorem analysis. Nevertheless, for some reason that you do not understand, for massless final state particles, the two effects cancel each other. Exactly. And as a result, there is no contribution to B mu nu for binary black hole merger, because for binary black hole merger, the final states are massless particles, okay, the gravitational waves that are flying away. But there can be appreciable contributions for supernova and other explosive events. One can turn this around and one can consider this null result that there should be no 1 over u term in the binary black hole merger is a test of general relativity. Okay, if you find a 1 over u term in the late time radiation from binary black holes, that signals a violation of the laws of general relativity. So I'll stop here. Thank you.
Questions for Ashok? Can I? Actually, I have two questions. Okay, I will say the first. So in slide 8, when you show the expansion of the memory, so just as a reference, how would look the quadrupole in there? Just the standard quadrupole radiation?
I think quadrupole radiation will fall off faster.
Sorry?
See, I think quadrupole radiation will fall off faster as a function of u, my feeling. So what we did here, this to get this term, that you took the memory effect, right, which leading order is like a theta function, right. So in Fourier space, the memory effect goes as 1 over omega. And then the backscattering gives a phase of e to the I omega log omega. Okay, so when you expand it out in Fourier transform, right, that gives a 1 over u term.
That leads me to the second point. So the logarithmic part, which is in the next two leading, it really smells like the tail of the memory, doesn't it?
It is a tail. Okay, part of it is tail to the memory, what we normally call the backscattering, right? But the other part, this part, right, has a very different origin. Right? This is not the usual tail to the memory. As I said, this is the result of acceleration of the outgoing particles at late time, and they radiate.
In the case of binary black holes, what would that be? What is the acceleration?
Oh, because the gravitational waves that are going out, they are being accelerated in the background of the original black hole, right? And they continue to radiate. So they have soft net radiation. Okay. And that radiation exactly cancels the one that you get by renormalizing the memory term.
Now you're saying that this can be tested. Do you know what sort of signal to noise ratios or when one might be able to detect it? It's up much higher order post-Newtonian effect.
Yeah.
Do you know what?
Meaning the order of magnitude?
Yeah.
Okay.
Yeah.
See, again, for binary black holes, of course, there's exact cancellation. Right?
Yes.
So you'll not see it.
Yeah.
So for supernova, for example, we did a rough calculation. If there is a supernova in our galaxy, right, then I think the detection is just at the age of LIGO detection, right? So for example, this 1 over u term will turn on at about a second after the peak, okay? And the strain is about 10 to the minus 22. Okay. But that requires a supernova in our galaxy.
But we could also do the null test.
Yeah.
Where we can look for this effect in binary black hole signals and see whether it's present or not.
Exactly.
And that would test GR.
Yeah.
Would you expect this term to be there in non-GR modified theories of gravity?
Yeah, for example, if this phase, right, if you modify this phase by, say, some coefficient, right, then this exact cancellation will not take place. Right? Instead of it's I omega log omega, suppose you multiply by some constant, right, then that constant will enter the final formula, and there will be no exact cancellation.
We could constrain that parameter.
Exactly. So you could constrain that parameter.
No, I just wanted, I understand that is 0 in the binary black hole case, but at which PN order, if you, I don't know if you think in terms of PN orders, but if you take the terms before cancelling with each other, at which PN order this effect will enter?
Yeah, I don't think in terms of PN order, right? Because this is calculating so this effect depends on the full radiation, right? So most of the contribution is going to come from the late radiation because it's a merger, right? For binary black hole, for example, the major part of the energy is radiated during the actual merger phase, right? Not in the PN order. And all these effects that we are seeing is proportional to the energy that the wave is carrying away, right? So in this sum, for example, in any sum of this kind, right, this sum is over all the outgoing gravitational radiation. Right? And most of the contribution is going to come from the merger phase. So PN order, you will see a little bit effect of this because some gravitational radiation starts going out at the PN order, right? But that's a very small fraction.
Yeah, but still we do test of the in spiral where the PN orders are, and we put
one PN order more than
one PN order. The memory is starting at 1.5 PN order. At 5 PN. Okay, so it's a 6 PN, would be a 6 PN term. This one.
Conservative dynamics.
I
don't know.
In the conservative, okay.
In the outgoing particles, is there an assumption that they should go other than gravity, there is no other interaction?
Well, we are assuming here that there is no other long range interaction. Right? If, for example, the outgoing particles are charged, there is electromagnetic radiation interaction, and that can be included. We have a formula that includes electromagnetic interaction.
But there is no inclusion of coherent fields that are carrying away momentum and energy. Like, for example, in the typical supernovae, apart from the neutrinos and baryonic matter, there's coherent magnetic field also going out.
Yeah, so that's included because in this sum, right? If this sum has to include over flux of all particles, right? So if there is a coherent field that is carrying away the radiation, that also has to be included in this sum.
In principle, that can be also.
Exactly. Yeah, so this sum includes everything, right? But the extra term that you have to add is if there is, for example, long range interaction other than gravity, right? Then that will contribute, and that modifies this formula.
I have one question. So you said that there are two possible sources. One is because of the acceleration, and other is the tail of the memory effect that are responsible. What other effects do you think might be relevant at this?
Well, the point is we have to make sure that so we have to bound all possible sources, right? When these particles are flying away, there is still gravitational field in between the two, right? And they themselves can source. They are sources of radiation. Right? So you have to basically show that the gravitational field that is still there, right, doesn't source this 1 over u-torn. We did a similar calculation for higher than d, right, where the calculation is much simpler because fields fall off faster. And there we found exact agreement between what we get from the soft theorem and what you get from direct GR calculation. Okay, and the two results agree exactly in higher than 4 dimensions. In 4 dimensions, it's more complicated to put these bounds.
Maybe I should know the answer, but I don't. So this effect I'm looking at, actually, Guillaume, there, has not been computed in post-Newtonian theory until now. And is it because you found at the end that it canceled for binary, so you didn't care about it, or because there was no calculation?
Yeah, if I understood correctly, but I am not sure, I have to think about it. It's a 4pn effect in the flux. So we will compute it soon. We are computing the 4pn flux now, and in a few months, this effect. Normally, it's inside.
But Ricardo is saying that there is a part of this effect which entered the conservative dynamics, but at 6 pn.
I think in the standard memory affects the waveform at 2.5.
No, but I was thinking about the flux. Well, this is the same. It's 2.5 for the flux, and then you add 1.5 pn for the tail. And so 2.5 plus 1.5, this is precisely 4 pn. So this is actually something we will include, I think, in our calculation. And if I understand correctly, it's there in the formalism, in the Bala-Iyer approach.
And so you were able to, on the other hand, compute this without, having to use techniques like PN, etc. Using amplitude scattering. This is what you said.
It's not even amplitude scattering. We basically have to look at the infrared part of the amplitude, because these, in the Fourier space, these are both singular terms. The memory, for example, is a 1 over omega, and the 1 over u part is log omega. So both become singular as omega goes to 0. And in the amplitude S matrix, it's easier to look for terms which are singular in the infrared limit, because there are very specific contribution diagrams which contribute to those.
I see. Also, you don't have a scattering, you are just an explosion of...
We also have scattering. This formula is also for scattering. This is also for scattering, where you have both incoming and outgoing particles. Right? The scattering really is no different in this. In the Fourier space, the scattering is no different.
You can always model two particles.
Yeah, yeah.
So,
yeah, this is independent of source dynamics, exactly.
so it is not sensitive to that at all. You are just specifying what the asymptotic form possibly can be.
Yeah, so as long as you know the asymptotic form of the particle momenta,
That's all that matters. So
this
whatever
result is
interaction
fixed,
is irrelevant.
Exactly. And the physics is also clear, right? Because as I said, memory, for example, is determined already asymptotic data, right? And this second effect, the second effect which renormalizes the memory effect, right, which is basically disperses the memory effect, that depends only on the memory term, right, and this phase, and a phase like this. So that's determined purely by the asymptotic dynamics. The other term is because of the long-range interaction between the particles, right? But that again is determined only by the asymptotic dynamics, because that takes over when the particles have gone sufficiently far away from each other, so that you can ignore everything else rather than the long-range gravitational force.
I don't really need to know what the sources are and what they are doing. I only need to know what are asymptotic particles, right?
Yes,
So
that's
therefore,
right.
I lose all handle on what the source dynamics is.
Exactly. Yeah, but the asymptotic particles, what kind of asymptotic particles will it produce? Of course, is determined by the source, right? Like this black hole merger doesn't produce any massive particle.
So if your binary is part of a triple, does it break your assumptions?
If my boundary is part of the?
If a binary black hole is part of a triple system, does it break your assumptions?
In a triple system, if you have 3 black holes.
Oh, no, it doesn't make any difference. Yeah, because all we have assumed is the initial system. For this formula, for the original formula that we wrote down here, right? Or this, all you have assumed the initial system is bound, right? Doesn't matter how many black holes there are. And finally, there are a set of particles which are flying around.
No, but I think the question is, because you said there is this cancellation, I believe this was the question. If there is still this cancellation that gives you 0, if you have a triple system.
Yeah, cancellation is all in the final state.
But then why for a supernova you don't have this cancellation? Sorry.
So because they are massive particles. For supernova, there are massive particles flowing out.
Particles, you mean matter?
Matter, yes, matter, exactly.
So then if you have a merger of a binary with a neutron star?
Yes, then you have this effect. Yes.
You have this effect?
Yeah. So neutron star by black hole merger.
So this could be a way of distinguishing binary black hole from a binary neutron star.
Okay, if there are no more questions, let's thank Ashoke.